Welcome to Statistics, Chapter 5, Lesson 1, the Introduction to Probability. So probability is all about exploring random processes. A random process is anything that generates outcomes that are purely determined by chance. So this is when you roll dice or when you put slips of paper into a hat and pull them out, or pull popsicle sticks with names on them. All sorts of things can be random processes. Remember, the big thing is that randomness is predictable in the long term only, but not in the short term. If you flip a fair coin, a coin that's equally likely to be heads and tails, 1 billion times, you will get something very close to 50% heads and 50% tails. Maybe not exactly, but no matter what the previous flips were, there's no way to know what the next flip is going to be. So that's the short term. Short term is, what's the next one going to be? I don't know. But what are the next 100 or the next 1,000 going to be? I have a pretty good idea of what it's going to be close to. Probability itself is any number between 0 and 1. 0 means this is definitely not going to happen. It's 0% likely. And 1 is definitely, certainly going to happen. That is 100% likely. And all of those numbers and the decimals in between represent the proportion of times that a given outcome will occur in a very long series of trials. Again, that's the long-term probability idea. If you want to make it a relative frequency, we can turn a probability into a long-run relative frequency by just turning it into a percentage. It's a percentage that represents the likelihood of an event occurring. And the law of large numbers kind of has two parts to it. First off, if you have a larger sample size, it will produce results that are closer to your true population values. So if you have a larger sample size, you will get something closer to the actual mean, median, mode, standard deviation, IQR, and etc. that you would get from a census by looking at every individual. Also, larger numbers of trials produce results that are closer to true probability values. So the more times you run a trial, the more like the long-term relative frequency or the long-term probability your results will be. And finally, we're going to talk about running and designing simulations. Now, simulation does not necessarily mean using a computer, although it will be a little bit easier for us to use our class computers here, the calculators. But simulation is just using any random process to mimic real-world outcomes. So when you are designing or making a simulation, you need to describe which random process you're going to use and how you're going to use it to perform one trial. You need to explain what you will record at the end of each of those trials. You also need to perform many trials, 30, 40, 50, 100 different trials. During class, a lot of the time, if each one of us in the classroom just does the trial 3 or 4 times, then all of us together do end up with that many trials. And then, of course, always use the results of your simulation to go back and answer the question of interest, answer what they're asking. So let's take a look at a few examples here. So right now, let's look at example 1, which I've actually got on the next page so that we have some writing space. So according to the Book of Odds, the probability that a randomly selected U.S. adult drinks coffee on a given day is 0.56. So what is that as a long-run relative frequency? Remember, relative frequencies are percentages. So let's say something like there is a 0.56 as a decimal, multiply by 100, or just move the decimal 2 places to the right. There's a 56% chance that a randomly selected U.S. adult has drunk coffee or will drink coffee that day. And that's really all you need to know for long-run relative frequencies. You turn them into percentages. It doesn't mean, so again, that does not mean that for any one person there's a 56% chance that they drunk coffee that day. It means that if I grab any random person, I have a 56% chance of finding out that they drunk coffee that day. So if a researcher randomly selects 100 US adults, will there be exactly 56 of them that day? 100 is kind of a lot of trials, but probably not. But we expect results close to 56 drinking coffee, since the long-term relative frequency is a 56% probability or frequency. Instead of because, but. And again, we're talking about US adults. Let's say there are 350 million people living in the US right now, about, probably more at this point. And adults count for pretty much all but about 21% of those. So the other, the other 80% are, so 20% are children, about 80% are adults. So that puts us at 280 million people. 100 is a relatively small sample. Compared to the full population of US adults. So next we're going to get into running and designing simulations. So if I were here live, I would have you guys use some dice, but I would also have you create a class dot plot. We're going to look at a couple of different versions. If you guys would like to create a dot plot during class, this would actually be a better way of looking at some of our results. So instead of using six-sided dice, though, we're going to use our graphing calculators and the random integer function. But example 2. As a special promotion for its 20-ounce bottles of soda, Sipsy Cola presents a message on the inside of its bottle caps. Some of the caps say, "Please try again," and others say, "You win." The marketing for Sipsy says that 1 in 6 wins. Grayson's class of 30 students buys enough 20-ounce bottles for the whole class, but only 2 students win a free Sipsy. So is that actually likely to happen? We're going to design and run a simulation using 6-sided dice. And then we're going to create a dot plot here. I've also got the dot plot from the book up here, so we look at that. And then we'll look at whether there is any convincing evidence that the company was wrong when they said so. So, our simulation design. So we need to say what random chance process we're going to use. So we're going to use a random number generator. And it's a class of 30 students. So we're going to pick from the numbers 1 through 6, 30 times. We need to say what counts as a success, what counts as a win. So we're going to say that 6 counts as a win. And we need to say what we are recording. And we are recording the total number of wins in a class of 30. And then the last part again is to go back and answer the question that they're really asking us. So let's look at what one trial looks like, and I want each of you to at least run one trial, but it'll probably be better if we run more than one. Be right back. My lights just turned off. There we go. Just needed to move around for a second. So you want to go to Stat Edit rather than running that single random number thing 30 times on your own. You'll probably want to go up and define a list, hit enter. Here, let's get all of the buttons here so you can follow along. We want the list to be math. Go to the probability menu, and we are selecting random integers. Again, there's a 1 in 6 chance, so 1 to 6 is what we're going to roll. And there were 30 people in the class, so we're going to roll it 30 times. So we only care about the number of 6s that show up in all of these trials. So I'm just going to go down the list and count up my total number of 6s. So I've got 1, 2, 3. I had 3 bottles of free soda in this trial. So if I was going to add this to a dot plot, and we would have the number line 0, 1, 2, 3, 4, 5, 6, etc. And I would just put my dot on 3 because I got 3 wins. Now, as a way of setting up for this, I've also run this simulation 29 more times. So I'm going to add my 3 wins to a list that I've already got stored over here, the soda list. So again, I ran this 29 times already, so this is my 30th. So we'll just put my soda list in there, and my last 3 goes in there. So the calculator doesn't really look at a dot plot quite so much, but we can turn this into a histogram. To make the histogram, we want to go, so I've just put all of my results into L1 now. I got rid of my rolls of 6s, which is why I have some numbers that are more than 6. But if you hit second y equals, we can take a plot and turn it on. We can make it into a histogram using L1. For this one, we want to set our window in a particular way. So if you quit out and hit window, so we expect our x values to probably be between 0 and 10, maybe 0 and 15. You probably want to set your y minimum to -1 or something like that, and your y maximum to 12 or 15, just so you can see the y-axis as well. And then when we hit graph, we should have something kind of like that. Now again, this is less useful to us because we see that we don't see any numbers here, but when you trace, so anything that's 0 with a maximum of 1, we didn't get any of those. Minimum of 1, we had one time that we only won 1 soda. N equals is the total in that count. So 2 wins we had happen twice, so it actually does happen in the simulation, and we can go across the rest of the thing. Again, 8 wins happened 4 times, 9 wins happened once, and 11 wins actually happened once as well. Now, if we look at the books dot plot, here, let me get out of the trace menu. The books dot plot looks something kind of similar. So what percent of the time did our simulation produce 2 or fewer prizes in a class of 30? So right now this dot plot has 40 dots in it. So whatever it is out of 40. So 2 or fewer prizes happened 1, 2, 3, 4, 5 times out of 40, and they asked about what percent. So this is for the textbook example. 5 out of 40 is 12.5% of the time. So it did actually happen in the simulation. If we look at my numbers, what percent of the time did we get 2 or fewer? Again, let me go back to my graph and trace. So 2 happened twice, 1 happened once. For a total of 3 times out of 30, because I only ran this 30 times, but they ran this 40 times. So 3 out of 30 is about 10%. Again, the 40 simulations is probably closer to the real percentage chance of that happening, of getting 2 or fewer free sodas, because it has a larger number of trials. I personally did a smaller number of trials because I was trying to set up what our I spent a lot of time setting up all of the list there. So is there any convincing evidence that SIPSI was wrong when they claimed that 1 in 6 wins? So 1 in 6 does win. It does happen. Basically, if it actually happens in our simulation, it is likely to happen in reality. So are they wrong about 1 in 6 wins? Well, 2 out of 30 sounds like less than 1 in 6. 2 out of 30 is 0.067, about 6.7%, as opposed to 1 in 6 is 16.7%. But because it happens in the simulation, or because it happens in the simulation, or probably going to happen in your dot plot in the class as well, then it should actually happen in real life. So they are probably not wrong. This is what I'm going to look for in a test or a quiz about, is there evidence that they were wrong? No. We got results of 1 or 2 free sodas in the simulation, so it should actually happen in real life. Or it could actually happen. Again, we got some simulations where 10 people won, or I got one where 11 people won. But that's example 2. Example 3. So in an attempt to increase sales of its popular cereal, Corn Sweets, Milner General decides to offer a NASCAR promotion. Each box of Corn Sweets will contain a collectible card featuring one of the following NASCAR drivers: Joey Logano, Kevin Harvick, Chase Elliott, Danica Patrick, or Jimmy Johnson. The company claims that each of the 5 cards is equally likely to appear in a box of cereal. Carmen, a NASCAR fan, decides to keep buying boxes of Corn Sweets until she has all 5 cards. And she is surprised to find out that it took her 23 boxes until she found her last unique card. So we need to describe a process. We need to design a simulation using a random number generator. So this one, they actually told us what tool we're using To perform one trial of a simulation that can be used to estimate the number of boxes of cereal that one would need to buy in order to collect all 5 cards. So let's use a random number generator to select numbers from 1 to 5, since there are all 5 cards. And let's again try 30 times, because that should be enough trials to actually get all 5 numbers from 1 to 5. And then we're going to count up how many different rolls it took before we get all 5 numbers from 1 to 5. Let me look back at my notes again to see what else we needed to make a simulation. We described which random process, how it's performing one trial, what we're going to record at the end. So next is going to be performing the trials and then using the results. So again, you can make a class dot plot. We will also look at the book dot plot. And I've also done this one 29 more times. So let's get rid of this list. Now to perform one trial, again, we're going to use random numbers generated, random integers, between 1 and 5. And again, just so I don't have to keep typing this in over and over and over and over again, we're going to run this 30 times. So I just want to see how many times rolling the dice or generating new numbers it's going to take me to get all 5 numbers, 1, 2, 3, 4, and 5. So it looks like I got a 1, 2, 5, 3, and 4, all within my first 5 this time. So sometimes it takes very little, sometimes it takes a long, long time. So again, this one took me 5 boxes of cereal. I need to add that to my dot plot. So again, 5 would be the minimum that it takes to get all 5. So I would just put a first dot there. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. She took 23, so let's go all the way up to 25. And then the rest of the class would just keep adding to their dot plot, to this whole dot plot. Again, I have preloaded a set where I'm just looking at the number of cards it took. I'll add my 5 to the bottom of that list. And I will replace this with my cards list. So again, this one, second y equals, we're already in a dot plot, or sorry, we're already in a histogram. It's already turned on, but I need to change my window so that my x values go up a little bit higher this time. And there's something that looks like my dot plot. So if I trace 2, 3, 4, 5 happened there. Now, she was surprised that it took her 23. Do we ever get 23 or more trials? 2, 4, 18, 19, 20, 21, 22, 23. I didn't get 23 trials. But I only ran this 30 times. It doesn't necessarily mean that they are wrong. It just means that I didn't necessarily run this enough times. Because if we look at the dot plot from the book, They ran it 40 times again. At least I think so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They actually ran it 50 times. So the book's dot plot ran it 50 times, and do we actually get, it took her 23, 21, 2. It never happened in the simulation for her, and it never happened in my simulation. So it is not very likely that this should have happened in real life. But what is the typical number of cereal boxes that it takes to get all 5 NASCAR cards? Basically, we're going to take this dot plot and find the mean, the average number of times that this is going to happen. So here, let's just make a new list and find the mean. We had 5 5s, 2 6s, 5 7s, 7, 8. We had 4 8s. 1, 2, 3, 4, 5, 6. 9s, 5 10s, 2 11s, 2 12s, 1, 2, 3, 4, 5, 6, 7 13s. Looks like 13 is going to be close to the typical number. Yeah. 3 15s. 3 16s, no 17s, 3 18s, a 20, and a pair of 22s. So the typical number is going to be the mean, the average. You could have just added all those numbers together and divided by 50, or since our calculator can do some of that for us, it should actually take about 11 boxes of cereal. But again, because it never took out of 50 here and my 30 there, so 80 trials, we never actually got 23 boxes to get all 5 of them. I bet there is a chance that they were not correct about the probability of each card appearing equally. Okay. And finally, example 4. If MA decides to raffle off 2 of the best, most desirable parking spots in the student lot, these are dubbed the golden parking spots. We have a total of 1,037 students who drive to school regularly in this particular year, and each of them is just given a raffle ticket. There are 62 students in Mr. Q's stats class. What's the probability that a fair lottery ticket selects both students from my stats class? So describe how to use a table of random digits to simulate this. So we're going to use a table. This is actually not a long enough line to do 3 trials. So let's grab one of our random number tables. Give me a second. And we're going to randomly select a number to start on between 101 and 200. We're going to start on line 112. We're going to start right here once we do it. So if we have 1,037 students, we need to, again, they told us to use the table. We need to look at our digits. 4 at a time. Until you get to unique numbers and just to make it simple, we'll start on 1 or 0001 and 1,037. 0001 up to 0062 count as Mr. Q's stat students. Zero, zero, zero. Sorry, 0063 up through our maximum of 1037 count as other students. And we will count up the total number of times that both of Mr. Q's students get the golden ticket. So again, this string of numbers is actually not going to be long enough. That's why we randomly decided that we are starting on line 112 here. And we need to perform 3 trials. So again, we're looking at this. Let me zoom in a little bit and focus the camera. We're looking at these 4 digits at a time. Let me get a pencil for this one. And we only care about numbers between 1 and 1037. So 5963 is too big. 6000 anything is too big. 0404 though, student number 404, is not in my class. So 6,347 is too big. 1,197 is still too big. 1935 is still too big. 2,730 is too big. 8,000 is too big. 8,000 is too big. 5,000 is too big. We got to keep going to the next line until we get our second student. So again, 6,000 is too big. 8,000 is too big, but 0640 neither of those is my stat students. So now we're ready to try trial 2. For the next trial, since we're using the table of random digits, we just continue along the same line where we left off. So 3,000 is too big, 3,000 is too big, 7,000 is too big, but 0225 works. But that is not one of my students. 5,000 is too big, 4,000 is too big, 1776 is too big, 4,000 is too big, 9,000 is too big, 9,000 is still too big, 7,000, 6,000, but 0381 will work. But again, neither of those is a number between 0 and 62, or sorry, between 1 and 62, so 0 stat students. And then trial 3. Again, just continue on the same line. So 9,562 is too big, but 0202, student number 202, is not one of my stat students, because again, that's not a number between 1 and 62. 93800915 does work, but again, 0 of my stats students actually made it there. So it is probably not all that likely that this fair competition would result in both of my students getting the parking ticket. Now, it's not impossible. It could happen, but it's not very likely to happen. But that was our set of notes for Chapter 5, Section 1, Introducing Probability.